Hi guys, hello everyone. So I'm Pekka Rossi from University of Oulu, Water, Energy and Environmental Engineering Research Unit. I'm here as an assistant professor nowadays, and then we have Anssi Rauhala here as a university teacher from the Structures and Construction Technology. And Anssi will be changing the slides here, and he'll be continuing the presentation after me. So Anssi, if you get the next one. So what we're talking about today is remote sensing, and mining environments are large surroundings where we have big areas that we want to monitor, and remote sensing can bring here a tool where we can have a holistic view of these areas in a wide perspective. And when I'm talking about remote sensing, I'm talking about, for example, satellites, where we have different options available, commercial or freely available, commercial ones like TerraStar X, and freely available like Sentinel or Grace as examples. Or we can have unmanned aerial vehicles, UAVs, where we take the drones to the area and make the flights and collect the data. And different types and different types are used for different area sizes. And then we can have ground leveled, just the ground-based UAV, ground-based remote sensing is also one option that's available. So that's where we have the methods ground-based, and it's collecting the data not from the air. And today we're concentrating on the UAVs, where we have a few examples we're going to talk about. And firstly about the environmental monitoring, where we have water quality and vegetation questions. And then on geotechnical monitoring, where we have substance and stability questions in mind. So Anssi, if you change. The projects which we have these results from are remote sensing supporting surveillance and operation of mines, an indirect route project, where we had University of Oulu, LTU from Luleå, and Norut from Norway on that project. And then continuing from that, we have a drone-based monitoring of mine environment led by Geological Survey, and also we have the University of Oulu there, where we have the next results coming out.
So first, let's talk about the environmental monitoring. So we have an example here of treatment peatland, same things that Uzer was talking in his presentation, monitoring of the water fluxes there. So study of how the effluent water that has been already treated comes to the treatment peatland before going downstream to out of the mining area. So we wanted to know how this treatment peatland works. Here's a view of the peatland. And if we change to the next slide, what we did, and here's a big picture of the peatland from above. So we have the distribution pipes on the right, and then a collecting ditch going through the peatland, and then we have a pumping station afterwards, and it's cut from the rest of the region with cut-off ditches from the surroundings. And the treatment area is approximately, as you can see on the down picture, the lower picture is the black area over there. So it's approximately one third of that whole area where we approximated the treatment area. And what we used there was thermal imaging, color infrared imaging, and normal camera, where we have the picture from above here. And that color infrared image, we could do a normalized different vegetation index out of them, so we could see the conditions of the vegetation based on that picture we get from the UAV. And for the thermal imaging, we could see if there's cold points there in the area where we would have groundwater seepage, for example. And how these look like, if we have the next slide, is here. So we have the same treatment peatland with the normal camera, then the color infrared, and on the right, upper right, and lower left, we have the thermal imaging, and then on the down right, we have the vegetation index based on the color infrared image. And what we're going to look at is a bit of the details. We will look first for the black boxes over there. You can see on the upper left image, and then we'll look at those white boxes for details, for the black boxes for the thermal imaging, and then for the vegetation index for the white boxes. So what do we see? Let's change the slide. First one is about the groundwater seepage. So in this wetland, there were points where there was groundwater actually seeping as a springs to the area and mixing the system. So there was more water coming into these places and mixing this treatment process from that perspective more than planned. So we found those with the thermal imaging, and they were rather visible in the thermal camera there. So that was one thing that we would have to take into account when we think about the fluxes of the water through the treatment peatland. And then the next slide was about the vegetation index. So in pictures A and D on the left, first we have those, you don't see them that nicely, but you have some stressed spruce trees there on the red dots there, which tell us that the effluent water is going that way. So the trees are stressed because there's excessive amount of water on the treatment peatland because we have the effluent coming there. So we know that, okay, this area is actually as the effective area. There is excess water, and we change the water balance in this treatment peatland, so it's working. And same goes for B and E, where we have stressed pine trees, which are shown also in the red dots there. But you have to be careful how you interpret these kinds of pictures, because you also have in the C and F pictures similar kind of red color, which is actually just a reflection of the water on the surface of the treatment peatland. So we have like small ponds there on the peatland, and those show the same color as a stressed tree. So you have to make the interpretation of what you're actually seeing there, and using other means also to understand what's really going on. But we could pinpoint there the areas with the stressed trees, and if you go for the next slide, you see that what it looks like in the ground. So we know now that this effluent was going as it should be. So it was spreading to this peatland as it should, and this area is working as a treatment process area for the waters as planned. And we used also other methods to confirm this. We use stable water isotopes from the water to be sure that this is actually the effluent water that was there based on the UAV measurements. Okay, Anssi, for the next one. So this was from the RESEN project, the first one, and this was considering the publication on the left. And I'll now give the turn to Anssi to talk about the geotechnical sides of the UAV monitoring.
Thank you, Pekka. Hope you can hear me. Okay, on the right side, we have another paper from the RESEN project, which concentrated on monitoring tailings impoundment from UAVs. And this was focused on subsidence of the tailings, but I will rather today focus on something new. Okay, so this is from our new LECAP project, and this is just a second. This is a drone-based 3D slope stability analysis of a waste rock pile. So here on the right side, we have the actual final model made from UAVs from the Hitura mine waste rock site. It's a serpentine waste rock. On this model, we used about 270 pictures and ground control points to first make 3D model. And then we are doing analysis of three-dimensional slope stability and comparison to traditional 2D methods. So here on the left side, you have a sort of a sketch of how the three-dimensional slope stability works. So we use different kind of sphere-shaped trial surfaces and try to see how safe the slope is on certain locations. So here's a comparison of 2D and 3D analysis on one cross-section. So first of all, factor of safety in geotechnical engineering. It can be defined on different ways, but one way is to define it as a ratio between the sum of the resisting moments and sum of driving moments. So basically, if we just look at this slide here, we can think about the resisting and driving moments. So the driving moments are basically gravity, which tries to pull this slope down, and the resisting moments are caused by the internal strength of the material. So if we define it this way, the slope is considered unstable if the factor of safety is below 1. But we also have another ways of looking at what is the kind of recommended factor of safety. So we can take a look at what kind of risk to human losses we have and what kind of risk of economic losses we have. So for example, if we have negligible risk, then we have we can try to get at least 1.1 factor of safety. If we have high risk, we want to be above 1.5. So here, just looking at this one cross section, this is the kind of like a traditional way of doing slope stability analysis. So you basically draw in this CAD-like interface, you draw the surface where the actual slope is, and then you test different slip surfaces and try to find the factor of safety. Here on below, we have the actual 3D stability done based on the drawn material. So we see that we actually have a much more comprehensive view of the stability. And also in this case, we see that here is the cross section. So in fact, we have more unstable area just next to the place where we chose the cross section. So here we see the whole area with different kind of failure volumes. So in this method, we basically define what is the minimum volume that can fail, and then we can try the area with different volumes. So here we see that with 1,000 cubic meters, we have a factor of safety around above 1.1 basically. So this whole waste rock site is about 2 million square cubic meters. And when we raise the failure mass, we see that with 5,000 cubic meters, the factor of safety gets bigger, and with 35,000 cubic meters, the factor of safety is even bigger. So here's just, I hope you can see a short animation how it looks in a 3D world. So we can get, like you see, much more comprehensive view of the actual site and where do you have the unstable slopes, and then you can decide if you maybe need to do some stabilization. But just to conclude, time is short. We have heard in the morning that there is an increased demand on social acceptability and regulation and so forth. So then also the site management and monitoring needs to improve. And in these presentations, because there's so little time, we showed only a few examples, but there are also many other possibilities. But to conclude, I want to remind that remote sensing is not a magic bullet, but it can help augment and improve to the traditional techniques and to make a comprehensive set of monitoring and management tools. Thank you.